Okay, so one way to learn about Earth's history from rocks and thus make delineations in the geologic timescale is by using layers of rocks, more formally called strata. And these strata can be of any thickness. They could be meters thick, like in an outcrop, even kilometers thick in some cases, all the way down to centimeters or even millimeters thick, where you need to use a microscope to or other tools to analyze them properly. And the science of studying layers in rock is called stratigraphy. And what stratigraphy allows us to do is look at layers of rock and determine their age relative to one another. So stratigraphy alone cannot say that this rock is, say, 50 million years old. It can only say that this layer of rock is younger or older than that layer of rock. And stratigraphers do this using a set of principles known as Steno's laws of stratigraphy. The first of these is the law of superposition. And the law of superposition says that in a sequence of horizontal rock layers, like these blue ones here, rocks that are on top, or layers that are higher up, are younger than older rocks below. So in the example here, which is actually the Grand Canyon, the Kabob limestone would be younger than the Hermit Shale. But what happens when you have tilted layers? Well, this is where the principle of original horizontality comes in. So with these purple layers over here that are tilted, if these layers are sedimentary, we can assume, just due to how gravity works, that these layers were originally deposited horizontally and then tilted on their side by some later geological event. And what this means is if we know the original orientation that these layers are deposited in, we'll assume sort of this way is up. We can then use the law of superposition on these tilted layers. So say the Bass limestone is older than the Galeros formation. The last one here is the principle of cross-cutting relations. And that principle states that if you have a feature like a fault or an igneous intrusion, if whatever rock it is cutting through must be older than the fault or the igneous intrusion. And that's simply because you can't have a fault cutting through something that hasn't been formed yet. So in this case, the igneous intrusion here, the plutonic complex, would be younger than sort of the brown colored rock in the diagram. So here's an exercise that you can do on the principles of stratigraphy. We have a number of rock layers noted by letters. We have an erosional surface G, as well as an igneous intrusion C. And what you can do is you can try and order all the letters from oldest or first formed feature to youngest or last formed feature. And you can check your answers using the link here. These slides are in the description of this recording. And there's also some other stratigraphy exercises you can do on this website. Definitely recommend thinking about this one for a bit. Now, I said earlier that stratigraphers can determine the relative ages of rocks. Now, in certain cases, you can actually get an absolute age for certain rock layers. This isn't really stratigraphy, but just something you can do in the field. And a good example of this is rock layers that were formed by a geologic event that separated two spans of time on the time scale, such as this darker rock formation here, known as the KT boundary, which separates the Cretaceous, the end of the Mesozoic, the age of the dinosaurs, from the Paleogene or the Tertiary, which is the start of the Cenozoic. So this feature, it can be seen in many parts of the world, including the Badlands in Alberta, and by looking at it, you know that the feature itself is around 65 million years old. The rocks below superposition are older, they're Mesozoic rocks. The rocks above are younger, they're Cenozoic rocks. So now you can start with features like this to start to add some numbers to your stratigraphy. Another way you can work with strata is combining the principles of stratigraphy with the fossil record. And this can be used to correlate strata that are found in different locations in the world. So for example, if you have two rock layers, one in South America and one in Africa, but they both have fossils of the same species, you know that both of those rock layers were formed sometime in the existence of that species, from the time it evolved until the time it went extinct or evolved into some other form. And for most species, this can be, a period of tens or even hundreds of millions of years, but there are certain species that were very abundant for a very short period of time, say 1 million years, that are, more useful for providing ages of rocks. But it's important to note also, when you're working with fossils, is fossils are any evidence of living organisms in the rock record. So you can have sort of fossils that preserve the organism itself, divided into types like original remains, like you'd find in a tar pit, chasm molds, carbonized fossils, or permineralized fossils in the rock, and you can look up what all of those mean. But you can also have trace fossils, and these trace fossils are indirect evidence, things like footprints, things like burrows, that an organism existed without actually preserving the organism itself. So fossils, any evidence of a living organism, whether it be the organism itself or their activities. But when you looked at the geologic timescale earlier, we saw that there are dates, there are numbers. So how do we go from relative dates to absolute dates? And what really revolutionized this was radiometric age dating. And what it does is it uses radioactive isotopes naturally found within the rock as sort of a clock to determine the age of the rock itself. Because once a rock is formed, for example, if it's an igneous rock that is solidified from magma, that starts the clock. And after that, the isotopes decay in a predictable manner following the half-life curve you see on the right. And if you know the half-life of the particular radioisotope you're measuring, and you measure the concentration of both the isotope itself as well as the atom or atoms it decays into, then we can figure out the age of the rock using this formula here. So Nt is a concentration of the radioisotope. Now, say carbon-14 is an example of one, a parent isotope, equals the initial concentration. So that's the parent plus the daughter, so what hasn't decayed plus what has decayed. And then also times 1/2 raised to T over the time of the half-life, and we know the half-life for carbon-14 is 5,730 years, and we can rearrange this formula and solve for T, figure out how old the particular object is. So there are a number of these radioisotopes that scientists use for dating various things. Carbon-14 is used for relatively recent organic matter. It's good up to about 70,000 years, but if you're dating rocks, what you really need is these last two here. Potassium-argon dating, half-life of 4.6 billion years, and uranium-lead dating, half-life of 1.3 billion years. And there are many other pairs as well. There are many different techniques using uranium. There's rubidium, strontium, just to name some. But you also need an isotope that's present within the rock itself. So if your rock has no uranium, if your rock has no potassium, it's no good. So it's a great technique, but there are limitations to it as well. So that's how we use different methods to construct the geologic timescale. Now we're going to take you through geologic history itself, starting in the Precambrian.